Okay, so in this next segment of the course, we are going to describe tagging problems. Tagging problems are of fundamental importance in natural language processing, and we will look at hidden Markov models, which are a widely applied type of model for this class of problem. So I'll first describe the tagging problem, and I'll give a couple of key examples from natural language processing of tagging problems. We'll then describe a very important paradigm for thinking about supervised learning problems. This is the paradigm of generative models or the noisy channel model. It's a widely applied methodology for developing methods for supervised learning, and we'll see it applied again and again in this course. Finally, I'll describe hidden Markov model taggers, which are one instance of generative models. We'll give basic definitions, we'll describe parameter estimation methods, and we'll describe the Viterbi algorithm, which is an algorithm of great importance in hidden Markov models. So this slide shows a tagging problem called part-of-speech tagging, which is a very important problem in natural language processing and is actually one of the very earliest problems considered in statistical or machine learning approaches to NLP. Statistical models for this problem go back to the late 1980s. So the problem is as follows. As input to the model, we have some sentence, some sequence of words. And as output, we have a tag sequence. What I mean by that is that in this output from the model, each word is now given an associated tag. So profits, for example, has the tag N, which if we look at the key stands for noun. Sword has the tag V, which from the key means a verb. At is a preposition, that's a P, and so on and so on. So the task is to take a sentence as input and to word by word assign a part of speech to each word in that input. So why is this in any sense a challenging problem? Well, it turns out that ambiguity is going to play a crucial role in this problem, as it does in many other problems in natural language processing. So let's look through the words in this sentence. If we take profits, for example, it's certainly a noun in this context, but profits can, of course, also be a verb in English. So if I say the company profits from its endeavors, profits is a verb in that context. Let's look for some others. Topping is a verb in this particular sentence, but it can also be a noun. If I say, for example, the topping on the cake. Forecasts is a noun in this sentence, but it can also be a verb. Quarter is a noun, but it has a much less frequent usage where it can also be a verb. Results is a noun, it can also be a verb, and so on and so on. So as a rough estimate, you might find that words in English, on average, can take 2 or 3 possible parts of speech. And this isn't only true of English, it's true in many other languages, probably most languages in addition to English. So here is a second example of a tagging problem, and this is the problem of named entity recognition. Again, this is a very important problem in NLP. And actually, in the first programming assignment for this course, you will build a complete named entity recognizer. So you'll build a model for this task. So what is the named entity recognition problem? The problem in this case is to take, again, a sentence, a sequence of words as input. And now in the output, we're going to identify named entities in the input sentence. So a named entity might be a company, or a location, or a person. Those are 3 very common entity types. And in this output, we've identified Boeing CO as a company, Wall Street as a location, and Alan Mulally as a person. So basic problem, take a sentence as input and mark up all the entities in that sentence in the output. So again, this is a very basic problem in NLP, and it's useful in a wide range of applications. You can imagine all kinds of cases where identifying entities would be a useful task. Now, at first glance, this doesn't look like a tagging problem, because a tagging problem needs to assign a tag to each word in the input. And here we really have a segmentation, an identification of subsegments of the sentence. But on the next slide, I'll show you how we can map this problem very directly to a tagging problem. So how does this work? What I've basically shown you here is the same example again, but where I've represented the segmentation I showed you on the previous slide as a word-by-word tag. So we have various tags. NA stands for something that is not part of an entity. So if you notice, we've tagged every word in the sentence in turn, and several of these words are NAs. They're not part of an entity. And then for the company entity type, I have tags corresponding to the start of a company and the continuation of a company. So if we look at Boeing CO here, we've tagged Boeing as the start of a company and CC as the continuation of a company. And similarly, we have Wall Street, which is a location. Wall is the start of a location. Street is the continuation. And Mill Alley, the same thing happens again. So what I've basically shown you here is that we can take the named entity recognition problem and map it directly to a tagging problem where we're going to tag each word in turn in the input sequence. So our goal is going to be the following. We're going to treat this as a machine learning problem. And so we'll assume that we have some set of training examples. And so this is actually a set of sentences taken from one very commonly used resource called the Wall Street Journal Tree Bank. And here we actually have close to 40,000 training sentences, where each training sentence consists of a full input sentence together with the underlying part of speech tags. And these training examples have actually been annotated by hand. So human annotators have gone through and sentence by sentence marked these kind of annotations. So that's a quite laborious job, but it does have the benefit that we have a readily available set of training examples for this problem. So the Wall Street Journal Tree Bank was a very early example of a corpus of this form, and now there are many, many other corpora across many languages and many different genres. So given this training set, our problem is going to be the following. We want to learn a function or algorithm that will take a new sentence's input and map that sentence to a tag sequence. So we're going to treat this whole problem as a supervised learning problem. To develop a little bit more intuition for how we might develop a model for this problem, or what kind of information might be useful in developing a model, I want to talk about two different types of constraints that play a role in the part of speech tagging problem, or actually any tagging problem. So, and I'll call these different types of constraints local versus contextual. So local constraints take the following form. If we look at a particular word of English, for example, can, and again we're considering the part of speech tagging problem here, can has a preference to be a modal verb. Okay, so it's much more often seen as a verb in English, but it can also be seen as a noun. So a priori, can has a bias to have one part of speech over another part of speech, and we'll refer to that as a kind of a local preference, the local preference of a word to take one part of speech over another. But we have to balance these local constraints against what I'll call contextual constraints, which are that some part of speech sequences are much more likely than others. So as one example, a noun is much more likely than a verb to follow a determiner. Okay, so if I have a determiner, the tag is DT, this is a word like the or a. After a determiner, I'm very likely to see a noun. NN is a noun. I'm much less likely to see a verb. Okay, so there's sort of contextual information. Some tag sequences are much more likely than others. And we'll have to balance these two types of constraints when we build tagging models. And it's worth remembering that these preferences are sometimes in conflict. So if I take this sentence here, the trash can is in the garage. And if I consider this word can, then can has a local preference to be a modal verb, but it's clearly a noun in this particular context. And that's because the surrounding words, the surrounding syntactic structure dictate that this really has to be a noun in this context. So two sources of constraints, local versus contextual, and we'll see that we can build a model which actually balances these two types of constraints.